Hello, this is Geoffrey Fox. I'm giving the introduction to Intelligent Systems Engineering E500 with a focus on my research areas, cyber infrastructure, clouds, high performance computing, their applications, and also a little bit of pure physics, because that's where my PhD was, and I still do work in that area. So this is the Department of Intelligent Systems Engineering, and this is the introductory course, which with a whole set of seminars covering everything in the department. All right, this particular recording is divided up into parts. This is part one, and it's got some global introduction and history from a long time ago. Okay, so a long time ago, I guess I was sort of intrigued by computers. Back in 1967, when I was starting my research, I'd had some experience with computers. I'd used them in every one of my research experience for undergraduates, or whatever they called it at Cambridge University, which I had each summer. And I was very fascinated by them. And I wanted to try to use them and to understand why they were useful. This needed to be synergistic with my PhD work, which was physics research, in particular high energy physics, or what's usually called particle physics research. And it's sort of interesting today, given how important big data is today, and people think it's only just happened. Back in 1967, my supervisor told me, nobody looks at data. I recommend that you do. So although I was a theoretician and I learned particle physics theory, I used that theory and learned that theory so I could do high quality data analysis. Now, physics is a little different from movie videos in that there is a sort of fundamental theory of physics. So there is some chance that you can build a rather reliable model. So I learned to use that theory to build models. Notice the theory for particle physics is not complete. You do not know enough to be able to predict what will happen in an experiment. All you know is some general principles which allow you to make a model with parameters and truths in it which can be compared with the experiment or fitted to the experimental data to learn useful things. So I then spent a long time collecting data. I remember the effort I spent. All the data was recorded as figures in physical review letters and physical review papers. And I even wrote a little Fortran program which was optimized for coping with logarithmic graphs, errors, and things like that. And I collected together more data than anybody else in the world had in this field. This was all, I accumulated published data, and my work in those days was called phenomenology. I would say that there are two problems with phenomenology. It's not typically used elsewhere, and also is rather difficult to pronounce. I still remember not being able to pronounce it in 1970, when I had a pretty well attended great conference in that area. I couldn't pronounce the name of the conference. So it's actually really better to think of this as data science, an early version thereof applied to particle physics or high energy physics. So this is actually the introduction to this conference I had. We had the proceedings. My friends Charles Chu and Tony Hay and I wrote this, edited this proceedings. We wrote an introduction, and this points out that data is impossible to calculate, but there are lots of ideas that are embodied in the models that must be respected in interpreting the data. And one of the reasons I build models is you can't actually put all the ideas that you need to respect in without building a model, because the model is a skeleton on which you can load the ideas. And this is not so different from today's big data. So models, which have important theoretical ideas, which are believed to be true, and then they might have some, you're trying to investigate some new theoretical idea to see if it's can be either found out from the data or checked in the data. And so I learned a lot. I even wrote my more or less first paper on how to do nonlinear chi-squared fits, which I was, in those days, I was only got up to 50 parameters and maybe tens of thousands of data points. But I probably did the largest fits of that type in the world in those times. Anyway, it pointed out that you needed to be a knowledgeable theory and knowledgeable experiment, and you needed to interact with all these sort of high points, what is used as the first and second paradigms of science, theory and experiment. And you're meant to be able to identify new experiments, show which ideas are correct. And even in those days, I was worried about funding. And in physics, it's even got worse. It takes many, many years to complete an experiment. And actually, a given graduate student often would have to graduate before the experiment is finished. That is actually one reason I left this field and went to computing, because computing seemed to be advancing a little faster, whereas physics was on this multi-year timescale, just constrained by the amount of time it took to build a large-scale experimental apparatus. Here is one of the apparatus I used. I built the simulator for this, which designed it and showed what parameters you wanted for these things here. This is a Cherenkov counter. Well, because when particles go through this medium, they emit light. So you count, by counting the amount of light, you can determine the mass of the particle. And so tell it whether it's a pion or a kaon. That was the main thing you were trying to do. Here we have magnets bending the charged particles, and you might have some sort of thing at the end to gather undetected energy. So this was actually a really, in principle, important paper, but actually it turns out this particular experiment, which this apparatus was designed to build, was no longer so interesting when we published the paper, and it was replaced by a new class of experiments, which is the other reason I switched field. That the particular things I was studying, so-called S-matrix theory, have fallen into not disgrace. They was believed to be correct, but it was not quite clear how you made progress, because they couldn't do winning experiments with enough statistics, because these models were still far from the truth. And so they did so-called high transfer momentum or deep physics, which studied quarks, and that has made huge progress. And in particular, at the much higher energies, we were doing this at the Fermilab. This was, you can see it in energies of 100 and 175 GeV. So at the large accelerators that people had, particularly colliding beams, they were able to get much higher energy and study more fundamental interactions, which were told you directly about the quarks and hopefully the gluons inside these compound particles, the pions, kaons, protons, and so on. All right. So I should say that that experiment, E110, which had a follow-on E260, had maybe 50 people on the experiment, and even then I thought it was large. But nowadays you might have 10,000 people. To look at the end result of years of work with graphs like this. This came from measuring cross sections, fitting the cross sections to a theory or a model, which here is called the triple Reggie model. It's a very famous model named after Giulio Reggie, who was a brilliant Italian theoretical physicist. Italy had always had and has very strong theoretical physicists. It was taken around 1976, and we got much better data than anybody else had ever had. These little dots here were the earlier measurements, which are restricted to this value here, the so-called value of momentum transfer T of minus 1.5. But we extended it out to more like T of 5 to 7, much larger T's. And we got these interesting structure, a giant dip, which was actually expected, well, sort of expected. It was predicted, but people didn't really believe the prediction. So this comes from what happens if you do great work at the wrong time. If we'd done this work 5 years earlier, it will be a hugely cited paper. Well, In those days, I used to do that analysis with Richard Feynman and a colleague, Rick Field, who's recently retired from Florida University in Gainesville. And Feynman taught me one thing. He said, when you're making models, do not change the model very often. You make the model, you study that model for 6 months, you write down the consequences of that model, and then you produce a new model. You do not change your model every day to fit the latest data. Some of you probably heard of Stephen Wolfram, who owns the company that produces Mathematica. Actually, the precursor of Mathematica was called SMP, Symbolic Manipulation Package. That was funded by my research grant, and I worked, in fact, for a whole year on that project before leaving it actually to go to parallel computing and the type of work I do now. This is one of my most cited papers, which is actually cited quite often still today because it's used in the analyses of modern data. Actually, why I'm in this sitting here today was I went to a colloquium. You know, you're always told to go to colloquium, but often don't. This was by a brilliant computer scientist. It was a physics colloquium, and this brilliant computer scientist, Carver Mead, explained why parallel computing was inevitable. So I listened to him, and then I started looking at the work we were doing on computational physics, and I saw that we could do it in parallel. And so this inevitability of parallel computing combined with the ability to do it in physics prompted us to build a parallel computer that was quite well known called the Cosmic Cube. That was actually built in the computer science department at Caltech, Chuck Seitz. But the physics department, the group led by me, wrote the software which did these early simulations. And then we built an application-oriented. I was and still am very interested in applications, and that was the Caltech Concurrent Computation Consortium or program, and we would also work with the Jet Propulsion Lab because they were engineers. We needed engineers to build machines, and so JPL, which was actually part of Caltech, was involved to build the hardware. So this type of work was pretty successful, but it still was hard and is still hard to actually make progress in interdisciplinary work. Here is the Cosmic Cube, and here's me probably looking a little more cheerful than I do today. This is Chuck Seitz here. Me. This was the Cosmic Cube. It has 64 boards. Each board ran at about a 50th of a megaflop. And it probably got 3 megaflops total, but in those days that was quite good. Then we built these follow-on machines. Here's the Mark II, built in 1985. This is the Mark I, you could call it, but really it's always called the Cosmic Cube, was 1983. And they were all single-board computers with memory, networking, and CPU on them. So, well, that was my early baptism of fire in interdisciplinary research. And it's still sort of essential, but it is actually, if anything, harder because everything you do is not only interdisciplinary, but globally located. When I was doing it at Caltech, I effectively had one collaborator in UCLA. I had collaborators at JPL, which were a few miles away. UCLA was probably an hour away on the Los Angeles freeway. So there were, but nearly everybody was at Caltech, and so that geographic co-location, which I didn't realize at the time, was very important. And it was sort of much easier at Caltech than in some places because Caltech has the best people. It doesn't have all fields, but you can find some good fields at Caltech, and if it's done at Caltech, the people doing it are among the best in the world. So we'll have to do these interdisciplinary works in intelligent systems engineering, and we'll probably have to collaborate not just at Indiana, but across the world, because that's the way the cross-world work has expanded a lot since I did this in the late 80s. So actually all this parallel computing work through around 2000 or 2005, in fact, was all simulation oriented. But then people kept telling me, let's work with industry. It's very important, Geoffrey, work with industry. And I tried to do that, but I didn't. And I even set up a pretty interesting project, Infoma, which had lots of good ideas in it. But it was too early. You know, when you do something, you better do it at the right time. I told you, I did my physics experiments too late. I did Infoma too early. I built the Cosmic Cube just at the right time because there were floating point chips came out just at the time I needed them to build those machines. At the time, I just diverted from what I was doing. I did lots of work on distance education, which was pretty successful. But I found that we tried to set up a company to exploit that, but we sort of got sort of somewhat destroyed by the quality of the internet, because this was around 1997, and we built systems which are similar to WebEx or Adobe Connect, and actually had some ideas which are still not in those systems. But you know, we had tens of kilobits per second. That's not good enough to do very reliable work. Anyway, I did try to do things like take the classes I had, which I was at Syracuse University at the time, and I tried to link it to minority serving institutions, and I taught them lots and lots of classes. And here is Infomal. You can see it's a virtual organization. That's a reasonably modern idea, virtual corporation. It had various components, education, software engineering, development, marketing, stores. It was actually really innovative, but it was too early, and we couldn't build it. I failed, sort of. Yeah, I failed. Here's a picture of me with Hillary Clinton. We were developing around that time part of this emphasis on more practical uses of parallel computing. We did telemedicine, actually pretty successfully, but we failed to fund that. There was some, if you go back to 1994 when this happened, there was some failed efforts in healthcare around that time, which meant that our efforts were not fundable. All right. That should have been more successful. I still don't, I must have made some mistakes. Here is me sitting next to my Silicon Graphics workstation, which was the state of the art in those days. And I was doing slides. I was doing actually sort of what I'm doing now, except it was done in real time, not asynchronously like I am now. I still had nice PowerPoint slides, which I used. This was one of the classes I taught called Programming for the Web. I also taught classes directly on Java. This was more on web technology. And here is Jackson State. Here's Willie Brown, who's my colleague at Jackson State. These are the students. And this is Nancy McCracken, who was from Syracuse but visited Jackson State. And I would say that was a success. It was not a failure. Okay. But I stopped doing it actually when I came to Indiana University, 2001, because somehow we didn't fit the model here when I came. All right, let's come back now. We've done that early history, so now we're in intelligent systems engineering, and what does it cover? Well, it covers intelligent systems, because that's why it has that intelligent systems name. Actually, that name was largely political. They wanted to find a word other than engineering because our friends up north at Purdue sort of coveted that name because they're so good at it. So, but intelligent systems is a good name because if you look at engineering studies systems, and nowadays the key progress in systems is actually the conversion of information to knowledge. That is an intelligent system. If you look at Microsoft and Google, they're AI-first companies, and that AI comes in this step here, when you go from information to knowledge. Information is sort of cleaned up, organized data. Knowledge is insight, and actually there are other steps, wisdom, decision-making, which follow from knowledge. and maybe raw data precedes data. But anyway, the examples we often give are self-driving cars, where if you go to Purdue, you can build the car. If you come here, maybe you can do deep learning to build an autopilot. And so, as all those intelligent systems are back-ended on clouds, that's why we have an emphasis on cloud computing and machine learning, which is the heart of the intelligent systems. Because we have a track in cyber-physical systems, and there are various predictions. Cisco said 50 billion things by 2020. Most people think that's a bit of an overestimate, but it's somewhere more like 30 billion. Depends quite how you define them, because a car has just lots and lots of things in it. And there are all these smart X, cities, vehicles, transportation, homes, cars, what have you. And this involves embedded systems, which is computer engineering, streaming data, that's the software side of computer engineering, and it requires modeling and simulation. You need to build a so-called digital twin. If you have a system, you want a model of it, which you can simulate. That's the digital twin, which Gartner thinks is very important these days. And we have a lot of effort in ISE and nano and bio and computer engineering in those areas. All right. So I do parallel and distributed computing, and when you think of those things, there are always systems, because they're sets of computers. And so when you're doing parallel and distributed computing, you're taking sets of computers, sets of software, and applying it to solve sets of things. Those things could be the parts of a car, or they could be the mesh points of a computational fluids calculation, or they can be the galaxies and stars in the early universe simulation. And when you do parallel computing, you always do roughly the same thing. You make up these parts from the problem. You start off with a problem like the universe. You divide the universe up into parts with patches. Or when you're doing a climate simulation, you take little blobs of a suitable resolution so that you get enough detail, and you look separately. These blobs, by the nature of the science, are linked to neighboring blobs, because you have differential equations which are usually local, and the general style of these parts is that they might be heterogeneous in their properties. Like the part of the weather that's a tornado is pretty different from the part of the weather that is wind-free zone, but they're still parts of the weather. And all that changes when you go to the tornado is that you need to make the parts smaller, because things are varying much faster. But that should be compared with distributed computing. In distributed computing, the parts are given to you. Like, you're trying to simulate the 20 billion internet-sized Internet of Things. Well, those 20 billion things are given to you. They're not. You don't have to chop them up. You don't have to chop something up to get them. And they also often are very different. Like if you take the robot and the back-end cloud controlling the robot, telling it what to do, those are pretty different. And all of these can be large. We have 20 billion things in our IoT, and you can certainly have that many mesh points or stars in your CFD or early universe simulations. So they're pretty similar, parallel and distributed. Both are consistent with parts. But the constraints are different because of the different nature of the parts. And when you look in detail about what's required, you will find that when you are building a computer system to do parallel computing, that computer system needs microsecond latency and high bandwidth between the different parts of the computer system. Whereas distributed systems can be simulated by distributed computer systems, and those distributed computer systems are bound to have milliseconds, because light takes 5 milliseconds to travel 1,000 miles. So they're always separated by milliseconds. And the fact that the If you're simulating a large-scale distributed system, which is intrinsically separated by milliseconds, you can then simulate it adequately on a computer, which has that type of separation. So when you do decomposition, you do what's called sharding. That's what you do in parallel computing. You chop the data set up into parts, or you can do it by function. Instead of taking a sort of homogeneous data set and chopping it up, you look at functions. You have a piece of data, say your pathology image. You could chop that image up into parts, but you could also just take that image and do functional decomposition. There's the function that cleans up the data, the function that clusters the data, and the function that visualizes the data. If you look at the sharded parts, the parts you make up by hand by chopping up the image, those are very closely connected and need this microsecond latency. If you look at the functional decomposition, those are loosely connected, and you can use much different computer architectures. There is a general principle shown on the next slide, which is a very old slide of mine. I gave a general theory of systems where were built around what you needed to do with systems for parallel distributed computing. And you will find that when you chop something up, the larger the part, the better it is, because the amount of interaction with the outside world, I mean, you've got a part, and then there's the outside world, the amount of communication compared to the amount of computation inside that part, that ratio goes down as the size of the system increases. It also depends on the dimension of the system, as shown on the next slide. And then you have to use all these principles to optimize some performance or ease of use, modulated all by the cost of doing everything. Here's this very old slide, and it's called the information dimension, which is often the geometrical dimension. You have a system. A complex system is just a set of things with connections. Everything is more or less that. Certainly a network, the internet is that, universe is that, computational fluid numerical formulation is that, and you'll find the communication goes like the work, and that work is raised to a power which is less than 1. And because it's less than 1, the ratio of communication to work goes down as the size of the work goes up, and it goes down with a power 1 over d. And that means that the smaller the d, the more it goes down. And for the very high dimensions, which we know is a tricky thing anyway, it doesn't go down as fast. All right, so there's something called Brent's rule, which says d equals 2 for computer chips. I say d is often geometrical dimension. If you do early university, you'll find d equals 1. There's lots of papers I wrote describing it. All right, so if you do systems research, you have to put several things together. Applications, algorithms, system software, hardware, and these are all different. And also, they involve different people. The people who understand the applications could well be different from the people who, say, understand the machine learning algorithm, or the computer engineers who understand the system software, and a different set of computer engineers who build the network and the computers. And, you know, putting all this together with the right expertise is very hard, and that's why data science has been identified as a key area, because data science brings together the multiple expertises to do this type of thing for a data-intensive or data-oriented system. Notice in all fields it's hard to get data. Data science is typically held up with a difficulty in getting enough data. And also, you really have to have an application expert. Even if you think you know the field, like I know physics. I was trained as a theoretical physicist, but I wouldn't. When I work on earthquake forecasting, I work with geophysicists who've taken their physics and focused it on the earthquake problem. Algorithms are a little different. You can do algorithms as a general concept. Sometimes they come from the application and sometimes from the generic person, and they can be generic application algorithms or application specific. Software comes in a stack, which we'll come to later. And we need to know what the geography of the whole system is pretty important. We have clusters, those are local. We have distributed. And then we have data streaming. If you have a distributed system, information or data has to go from one part of the system to the other. It has to go from the robot to the cloud. So that's called streaming data. Very important area. And we pointed out streaming data is milliseconds. And in fact, if you're streaming to the cloud, it's probably 100 milliseconds because the cloud application takes a while to wake up and do anything. And you need to know what style your hardware is. Is it like the Internet of Things? Is it like a cluster? Is it distributed, or is it all of them put together? It's a cluster joined to an IoT, and they're both distributed. And you need to worry about the structure in both the software and the hardware.